We should be live, I think. Hey there, hi there, ho there,
It's
everybody.
custom life.
Yeah, you're as welcome as can be to OpenCV Live episode 166, if you can believe that. Please, as you join us wherever you are watching this fine program, let us know where you're joining us from. We love to see the global OpenCV community chiming in every Thursday morning. This one is going to be very educational, and we're one of the things we love to do on this show is give away things to you for free, and we're giving you a sneak peek of the very not free Vision Summit workshop that our own Dr. Satya Malik will be participating in. We'll talk a bit about that at the top of the show here in a few minutes, but before then, yeah, just let us know where you're coming from. I'm coming to you from beautiful, fragrant Soma in San Francisco, California, and our stalwart host, Dr. Satya Malik, is joining us from.
From San Diego, California.
Yes, indeed. I see Basingstoke, UK. Hello, Chicago. Hello, Brussels. Hello, Pretoria. Hello, Togo. Hello, Florence, Italy. Hello, New Jersey. Hello, Ireland. Hello, Tucson, Arizona. Hello, India.
Hi,
Namaste, India.
India. I was waiting for you to
Oh, I
mispronounce
ain't
it.
doing that one. You want to do it? Go ahead.
Vishakhapatnam. That's how
All
it's
right. Oh,
pronounced.
yeah, no, see, easy one. Yeah, totally.
All right.
That's exactly what I was going to say. Hello, Mexico. Hello, Moscow. Hello, France. Hello, Chicago. Big fan of Chicago. Born and raised a Cubbies fan and the Bulls. Hello, Boston, Mass. Hello, Virginia, Ecuador, Bhutan, Switzerland, India again, Johannesburg, more Arizona, as Laszlo Cravensworth would say. Hello, Madrid. Soma is in downtown San Francisco, for what it's worth. It stands for South of Market. Hello, fake London, Ontario. No, I think it counts as real London. I've
Fake
been to London,
London.
Ontario many times on the way from Michigan to Toronto. Yeah, go Sox. Or were those socks? I can't tell if he's talking about the Red Sox or the White Sox. If it's White Sox, it's Go Sox. If it's Red Sox, it's Sox. Hello, Palm Beach. And looking over on LinkedIn, we've got on Twitch, we've got Paris. We've got Ecuador on Twitch. We've got Stuttgart on YouTube. Brazil on YouTube. Serbia on LinkedIn. Algeria on LinkedIn. Berlin on LinkedIn. We've got Ivan says hello on the YouTubes. And another Phil here in Zoom says good morning from Los Angeles, the city of angels. Your boy is having some phlegm issues this morning, so please forgive me if I have to mute out or if I sound a little bit logy here.
All
I
right. Should
think
we get
on
started?
that note, yeah, now's a great time to start.
Hello, everybody. Welcome to OpenCV Live. Today, we are going to present a tutorial on VLMs, which is Vision Language Models. And this is a very small tutorial. This is actually a small section of the tutorial that I'm going to present at Embedded Vision Summit. That will be like a full 3-hour workshop. So this is part of that workshop. If you live in the Bay Area or if you are attending Embedded Vision Summit, I highly recommend that you please come and visit us at the VLM workshop as well. So before I begin the show, as always, with me is Phil Nelson, who is the Director of Content and Creative at OpenCV. He produces the show. If anything goes wrong, even if I mess up, it's his fault. Hi, Phil.
Yeah, no, hey, that's the producer's job here. It's me. It's PHI LLIP. I am your co-host with the co-most, the second banana, who is second to none. I'm also your plus one and only. It's Mr. Nelson, if you're nasty, but you, my dear friends, can call me Phil. And I'm here to remind you of a few things that we do on every single episode of this here program, which is currently entering your eyeballs. One of the things we do is a giveaway to you out there in the audience. Stay tuned later on in this very episode, in about 40 minutes or so. I will be asking a trivia question to the Zoom audience here. If you're not on Zoom, you can get there by going to opencv.live. That's opencv.live. It'll just pop open your Zoom client, and you can participate in trivia in about 40 minutes. The winner of that trivia will get the OpenCV University course of their choosing. OpenCV University courses are heavy-duty material, folks. These are not things that are going to take a weekend to seemingly teach you everything, as a lot of these YouTubers claim. These are industrial strength courses made by people in the industry. These will take you some weeks, some months to complete, and when you complete them, you will actually know what you're doing. I know it's a radical concept, but we do our best here. We're also taking questions from you in the audience, and we will do our best, as the late, great Satoru Iwata would have said, to answer them directly. Use the Zoom Q&A button at the bottom of the screen to ask your question at any time, or just use the chat system wherever you're watching. We are live on YouTube, Twitch, LinkedIn, and OpenCV's Zoom channel. So keep the questions coming. I will do my best to interrupt Satya's presentation to ask them if they make sense during the show. We'll also save a little bit of time at the end for those questions. Before we get fully started here, there's a bit of business we got to take care of here at the TISOP of the Shizzo. And Satya's a busy man. You've got a lot of talks to do. We've got a lot of events to prep and invite people to. The first thing we should do, though, is thank our sponsors and tell people a little bit about how they can support OpenCV. Satya, you want to help me out here?
Yeah, so first of all, I want to thank all our gold members. So OpenCV is supported by, there are various mechanisms, but one of the primary mechanisms is our partners and members, the gold members, silver members, and bronze members. These are large companies who support us. And our newest entry, we have to update this website, is FutureWay. FutureWay is also now a gold member. If you work for a large company, please encourage your manager to look into it if they can support OpenCV. Usually, many large companies have these programs. And recently, I think a day back or so, we got a new bronze member. Phil, do you want to talk about it? And this was, based on some employee going and talking to their managers, if I'm right, Phil?
You're talking about Carl Zeiss?
Yeah, Carl Zeiss.
Yeah, so this was an interesting, this was one of those interesting things where we got an email to the contact form, basically. And Nicholas from Carl Zeiss AG is, one of the premier, if not the premier, optics manufacturer in the world. They've been creating lenses for cameras and medical equipment for like 150 years. It's a huge company. If you've got a camera, it's probably got a Zeiss lens in it if it's worth a damn. They're huge. They sent us an email that apparently OpenCV won a donation contest internally at Zeiss. We were one of I think they said 3 open source organizations that were voted on by the employees in a couple of the business groups that use OpenCV heavily. And so they're making a donation of 5,000 euros. We really appreciate it. Super exciting, unexpected. It's nice when you open your inbox and there's a check for $5,000 in there. It's pretty sweet,
Right.
Thanks to Zeiss.
Yeah, so the point is that if you talk to your manager about OpenCV, donating to OpenCV, then maybe the discussion's always going on about supporting open source, and we may just get lucky. So
yeah, absolutely, that's right. And if your company is large enough, it's very likely that they are part of a platform like Benevity or something similar to it. Benevity Causes is a system whereby large organizations like your Metas and your Facebooks and John Deere and Microsoft and all those kind of big organizations will do matching donations often for nonprofit organizations such as OpenCV. Sometimes these can take the form of cash, or if you donate your time by working on the library, sometimes they will even match that value in cash to the organization as well. So if you work at one of those big groups, help your boys out at OpenCV. We're doing our best to give you as much for free as we can, but sometimes we need a little bit back from the companies that make tons of money off of this open source software. I'm looking at you, Tesla. You can also, for example, become a member organization. We've got 3 levels of support: bronze, silver, and gold for different kinds of companies. If you're a little startup, scrappy startup, maybe just become a bronze member. If you're an established company, help us out by becoming a recurring silver member. Or if you're a large org like FutureWay we just talked about, become a gold member, a heroic gold member for $100,000 a year. That pays for a lot of the stuff that we do and a lot of the stuff that we give away to everybody else for free. You can also buy an OpenCV t-shirt. You can sponsor us on GitHub. We've got 17, count them, 17 sponsors
Oh,
on
that
GitHub right
increased.
now. Yeah, I'm pretty excited about it. Let's give them their 5 seconds of fame.
Awesome.
Kostub.
Yeah.
We've got ecosystems, the concept of ecosystems. We've got Rungia. We've got DJ Greenwood. He sounds like a musician, right? We got Ruda's Laboratories. We've got Tala Hussein. We've got Forodo. We've got, it's the second time I've said that weird. We've got Pedro Juarez. We've got the homies at RoboFlow, who I just saw were on a podcast with NVIDIA, by the way.
Oh, nice.
Alexander Ismailov, yeah. Comet ML. Haven't heard of these guys before. We'll have to check them out. Jonas Heinle, looks like. Got Nick Libertini, longtime supporter on GitHub. A Blue Jay, longtime supporter. Jesus Anaya, another longtime supporter. Got Alexandra Pomero, something like this. And we've got Victor Vedavoto, another longtime GitHub supporter. That's $9 a month. Huge shout out to these people. We really do appreciate it. Extra one of these that we get makes other people a little more likely to support to a certain threshold. If you go onto the page and there's like no sponsors, people are going to be like, it's not worth it. If you go on there and there's like 5 or 10, they're going to be like, maybe I should help them out. So please
Right.
throw us a couple bucks if you can. We've also got OpenCV t-shirts, 20% off everything currently, including the iconic import CV2 t-shirt, hoodie, hat, bag, whatever you got, whatever you want. It is available there for the low price of probably like $40 or something. Consider it a donation to OpenCV that you also get a shirt for. It's like the NPR tote bag. That tote bag did not cost $50, folks. It's about $5 worth of tote bag and $45 worth of donation. We've also got the I Love OpenCV design in Spanish, simplified Chinese, and in English. Put it on your dog, put it on your bag, put it on your small children. They probably won't figure out how to take it off. It'll be fine.
All right.
Also, important right now, the OpenCV SID Conference on Computer Vision and AI is a full day of talks focused on the past, present, and future of computer vision and AI, hosted by the world's most popular computer vision library, that's us, at Display Week, the premier international event for electronic display technologies. We are so excited to partner with Display Week on this conference. Saidi, can you give us a couple sentences about how great this is going to be?
Yeah, so Display Week, actually, there are about 7,000 to 10,000 attendees every year. Our conference, this is in collaboration with them because we have some good connections with them, and they were very generous to provide us with the space. So this is our first full day conference, and if things go well, we will do this more often, which means every year. And so please come and join us. There will be full days of talks. You'll get to meet us. There will also be there's also a workshop that I'm doing in collaboration with Display Week. Just one day prior to this, May 11th, I have a 2-hour workshop on image segmentation. So if you want to learn about that, please show up. It's a very nice conference, and if you can really help us by participating in this conference, and that will help us do it more, on an annual basis.
Yes, absolutely. And a hilarious comment here in the chat from Damien LaRoque. It looks like OpenCV is the FFmpeg of vision, or is FFmpeg the OpenCV of video? I think we've been around about 10 years longer. So I think technically, but huge fan of FFmpeg for what it's worth. Also, the VLC team are doing incredible things at trade shows. They're giving me some very dangerous ideas. So please come to the OpenCV SID conference on computer vision and AI. We're calling it OSCA, OSCCA. Yes, I'm a fan of Evangelion. That's why it's called that. We've also importantly got coming up another. Speaking of workshops, the workshop that you're getting a sneak peek of today in just a few moments is happening at Embedded Vision Summit, Tuesday, May 20th. Embedded Vision Summit is a conference we've gone to I think the last 4 years,
Yeah.
3 or 4 years. We have a booth there. You got to drop by, and I'll have some stickers. I'll have some buttons. I'll have some chit chat. It'll be a good time. Do some glad handing and some talking. Also, get yourself some buttons and stickers. Can you give us a couple sentences about the full workshop here before we get going?
Yeah, so this workshop is on vision language models, and I will give you a sneak peek of part of that workshop today. This is, as the name says, you'll learn a lot about what vision model language models are, because it's not one thing. When we talk about, uh, let's say, a classification model, it means usually that input and output are the same, but vision language models are not the same. When we say something is a vision language model, it can mean many different things, right? So we will talk about how to use a vision language model to solve problems. Including zero-shot classification that I'm going to talk about today. And also very interesting applications. You'll see some real-world applications where you take a single image without any training. You are able to do some fine-tuning very quickly and produce a solution. And this is on Tuesday, May 20, 9 a.m. to 12 p.m.
Yep, a little bit longer than this one. It's going to be
Yep.
jam-packed. We've also got the bin picking challenge. The perception challenge for bin picking is still ongoing over at bpc.opencv.org. There's just a few weeks left to participate in the development phase, which you will need to submit to in order to continue to participate in the other phases. So if you're part of a team and you have been sitting on the fence not submitting, you should probably get on that. And to help you, to give you a little extra motivation, we've got 19 teams here on the board right now. I think I see ICANN AI, another that they have participated in some previous OpenCV competition. I like it.
Yeah.
We've got 19 teams on the board. The MAPs not really moving very much. I think these are a lot of teams submitting the baseline just to get up on there. But we're going to do a little bit something extra to encourage these teams to submit and to put their weight on it, as they might say. Satya, can you tell us a bit about what we're going to give those folks?
Yeah, so we want this leaderboard to be moving. Right now, people have just submitted the baseline, and that is why these numbers look so low. For every week, right, the team that is on the top of the leaderboard for the next 3 weeks, we are going to give. So basically, we'll evaluate Friday. Just at the strike at midnight, we are going to evaluate which team has the highest, who's the highest on this leaderboard, and this is specific time, and that team will receive $200 cash in prize.
That's right.
So
Each week for the remaining weeks of the dev cycle here, we will be giving away $200 to the top team. Now, there's a couple of rules to keep in mind. The first of which is your submission here has to beat the baseline. It cannot just be the baseline submission. We're on to you. We're on to you, you engineers out there. Always trying to find a way around the rules. Also, it must beat your previous submission. You can't just, if a team, for example, is at the top of the leaderboard for week 1 and they don't submit any updates for week 2, they will not win the $200. It'll go to either nobody or the second team. We haven't actually decided. I guess the second team. So yes, please submit out there, folks. We've done a couple of Q&A sessions. We'll do another one in 2 weeks' time. Tuesday, it'll be Tuesday, April 15. Tuesday, April 15, which not an important day at all in the United States.
right.
It's tax day. Dun dun dun. Join us then. We will be doing another Q&A. If you've got questions, please ask them in the Slack channel. Ask them on the forum so people can find those if they have similar issues. But congratulations to the teams that have submitted already. You are in the running. I hope that your MAPs get a little bit better, and maybe you'll win a couple bucks. We've also got, quickly, man, where's this taking forever this morning? We got too much going on, Doc.
Okay.
OpenCV is on Blue Sky. You can find us. We're at OpenCV on Blue Sky. We're at OpenCV at mastodon.social. And I'm going to shut up now.
All right. Yeah, today was long. Sorry about that.
We're
Okay,
so
let's
busy,
get
man.
let's get. Oh, we also imposed a tariff over the Just kidding.
That's right. OpenCV is now 25% more expensive across the board, except for education, where it is 50% tariffs. It's going to cost. You're going to have to multiply 0 times 0.5, and tell me what the calculator says when you do that.
Get along with this. Now, why is it not showing my screen?
Yeah, it says it's
It's
loading.
loading.
I don't know, man.
What?
Here,
Really?
try unsharing and oh, there it goes. Okay, maybe
No,
you
no.
can.
I mean, if I okay.
Oh, there we
Good.
go. Okay, we got
All
him.
right. So
We
this
got them.
this presentation is part of this Embedded Vision Summit workshop that I'm going to do, and this is just a small part of it. But hopefully, we'll get enough value out of this. You'll learn something about a vision language model called CLIP, right? So CLIP stands for Contrastive Language Image Pre-training, right? That's a mouthful, but we will learn what exactly means, what contrastive means in this context, and what does image pre-training mean, okay? So
There's a reason
this,
they decided to call it clip.
yeah, so this is probably the first vision language model, which was, it has been used in so many different applications now, a very, very powerful concept. And you'll see how the ideas of, if you want to build a multimodal AI, then it needs to be able to consume text, images, as well as speech, etc. So here you'll see in this presentation how one of the ways in which you can combine these modalities, right? The vision modality as well as text. How do you combine these two things to build an AI model, right? So CLIP is obviously multimodal, right? It has two components, vision and language, and it is trained on image caption pairs, right? And it basically, so if you look at these examples that I have put in here, you can see an image and there is a caption. In fact, I was making these things in PowerPoint, and PowerPoint has this option to get the caption, right? These are stock images inside PowerPoint, and I just took those captions. So here we have a man wearing a mask, and the caption says "man wearing a mask," then colorful buttons, etc. Right? And you may be thinking that, okay, that's how do we get these image caption pairs? So the internet is full of image caption pairs because for SEO reasons and also for accessibility reasons, people when they look at if you look at the website, you see an image. Usually, I would say 70% of the time there would be a text associated with the image. It is called alt text, right? So in the web page, and the reason they put in alt text is for SEO reasons, right? Your earlier people were not able to interpret what the image contained, and so they would the alt text indicated what is actually present in the image, and that is how robots they were able to uh, figure out what's in the image.
Interestingly enough, this is a side effect of what they were originally created for, which was for screen readers, for people that
Yes,
have vision problems
vision
or
problems.
just simply are blind or are
Right.
visually impaired in the extreme and can't see stuff. And the alt text was there to describe what the image is for folks that are using screen readers. That's why it's really important when you're posting on Blue Sky or Mastodon or any of these social media sites. When you upload a photo, there's that little tab. It's actually really important for you to fill that out. I think
Yeah.
a lot of people don't because it's like one extra step in between you and posting the thing you want to post, but it's really meaningful and important to do. So it's a very small thing you can do for a huge accessibility improvement for folks out there that are have issues with their eyes.
Right. Plus, the good news is that some of this may be auto-generated, and then you can modify it in near future, right? That image captioning is very well. It's a technique that is very sophisticated now, right? The state of the art is very sophisticated.
One of the
But
few like pretty good existing like AI uses of like AI models right now is generating alt text that people review. I think
yeah,
it doesn't get enough attention, but I think it's pretty valuable.
right. And then, so this also, the goal. So all vision language models, right? They have different goals. The goal of this vision language model was zero-shot capabilities, which means that you should be able to identify what's in the image. Let's say you can train a classification model without actually having any data, right? You don't require any data if you want to use CLIP for, let's say, cat detection, right? Or you want to build a classifier. Given an image, it outputs one of the few classes, right? Like, let's say, cat, dog, horse, etc. You actually don't need to train anything, right? I'll show you an example how to do this, but CLIP specifically was designed for this zero-shot capability. Now, how does it work, right? First of all, the scale of the data set is large, right? It has, I think I left the million out. There are 400 million image text pairs. There was a mistake. And
That's almost 500 image text pairs. Can you believe the scale of the internet these days?
right. And the word count in this text is the scale is similar to GPT-2, but unfortunately this data set called web image text, it's not publicly available, right? The training time, it's about 18 days on 592 V100 GPUs, right? And so that's quite substantial, but not the end of the world, right? These are still manageable. For large companies, this is still a manageable expense. And there were two different backbones, right? You could use a ResNet backbone, which means this is a traditional computer vision convolutional neural network, or you could use a VIT, which is vision transformer based backbone. The vision transformer, it was in 12 days, again, using 256 GPUs. So it does take a lot of GPU hours, but still, manageable. It's not like years or months of training. So let's see how CLIP works, right? So the first thing is that there are two parts to it. You take the image and there is a vision encoder. And vision encoder is nothing but, you can think about it as the convolutional layers of ResNet, right? So you pass in the image and it will give you a vector, right? Here I've used a small vector. Usually the vector size is 512 or so in CLIP. But here I'm just showing it just to give you an idea what the vector could look like. So the idea is, given an image, you're converting it into a vector of a fixed size, any image, right? How it is done, we'll come to it, but it is basically using the convolutional layers of something like ResNet to create this vector. Now, on the other hand, for text, you're doing exactly the same thing. You are using a text encoder, which first, when you give a text string, it tokenizes the string, which means that it breaks the string into tokens, which you can think about them as words. And then you use the text encoder and you get a similar sized vector out of it, right? Now, so this kind of embedding, it's very standard, just like vision embedding is very standard, right? You can take an image, convert it into a vector. The same way you can, text embedding is also very standard. There are these pre-trained models that will give you these embeddings, right? Now, the important thing in CLIP is that they are the same size, right? This vector is 512. This vector is also 512, right? The idea is now that because they are the same size vector, you can think of them as points in a multidimensional space, right? And the idea is that you need to embed them in such a way, right? You need to train the model in such a way that these two vectors, if they belong to the same correct pair, right? You can see that this is a person. During training, you give this example, right? A person wearing the image of this person, and then text. If the text and the image, they match, you can calculate a cosine similarity, and you can see that, okay, they are close to each other, right? The objective of the training process is to bring these two vectors close to each other. On the other hand, if you look at this image is not a person wearing a mask, right? But the text is a person wearing a mask. So these two points, right, in this multidimensional space, we want to separate them, right? So that is the objective of the training process. The image text pairs, which are for the same entity, they should be close together. And those which are not, they should be further away from each other, right? That is the goal. Now here, I'm just showing it again. So the way it is done is that you take a batch of images, right? You take a batch of n images, and this batch size, this is quite large batch size actually. As far as I remember, it is in the 10,000 or so, that kind of number. So you take those images and then you maximize the similarity between n correct pairs. So think about this as image embedding, right? The blue one, and the orange one as text embedding. And this, I'm representing this multidimensional space using 3 dimensions only, just for clarity. So just imagine that you have a multidimensional space which is 512 by 1, right? That is the size of the dimensions. But here we are just showing it in 3 dimensions, so that because we cannot imagine beyond 3 dimensions, right? So the idea is that these pairs, when they are close to, when they belong to the same entity, right? They are matched, then they should be close together, and they should be as far away as possible from other pairs, right? That is the objective of our training process. So here we are showing this is a screenshot from the paper, and this is exactly what we are doing. We have some text encoding, and we get this encoding. We have image encoding, and if they are the same, then we should get a very high similarity. Otherwise, we should get low similarity. So the loss function, you can see it looks complicated, but it is actually not. If you look at it, you can see that it is basically, the similarity is a cosine similarity. You take the dot product between the 2 vectors and then divided by the norm of the vectors, right? And so basically, you take any vector, normalize it first between 0 and 1. So the length of the vector is is actually 1. So it becomes unit length vector. Once you have 2 unit length vectors, you can take a cosine distance. You can take a dot product between them, and that gives you how close they are, right? So if they are exactly overlapping, then the cosine distance would be 1. If they are completely orthogonal, then the cosine distance would be 0. So here we basically take all the, you take the distance between image to text, and then the loss between, text to image. You combine them and you get a single loss, which achieves this goal, right? This is our goal, to minimize the distance between pairs, the right pairs, and maximize the distance between the wrong pairs. And this loss function achieves that. All right, so how, let's look at this architecture a little bit, right? So the vision encoder, it is a ResNet 50 model, convolutional network, or a vision transformer, right? Think about these as backbones, right? Which basically convert an image. You take an image and it can give you a single vector that encodes the image, okay? And the output vector is 512. Here, in case of text encoder, we have a 12-layered transformer, right? Which is, it's very similar to the one that is used in the GPT-2 architecture. So in text, we always, transformers are the most popular one. In vision, both of them work just fine. Convolutional neural networks or vision transformers, both of them work equally well for this particular task, right? So that's the backbone which is used for converting the image into a vector and the text into a vector. The interesting thing here was that there was no cross-attention layers, right? Which means that the text was independently encoded, the vision part was independently encoded, and during the training process, they were they were brought together, right? So, which is very unusual, and I think this was because initially this was sufficient. First of all, people were just surprised that this kind of thing actually worked. But in subsequent models, let's say the Flamingo model from DeepMind, they used cross attention layer, where the image and they were connected. The image and the text embedding networks, they were connected. So the training procedure, right? They are trained from scratch, which is again a little bit surprising to me. But so they did not use any ImageNet weights. They did not use any NLP weights, which means that the training process. That's why it took that long. I'm not 100% sure what would happen if you had used ImageNet weights, and why they decided not to use ImageNet weights for Resident 50, because that's readily available. You could have started, and maybe the training process would be faster. But for whatever reason, they chose not to use those weights and trained everything from scratch. So the mini batch size, when they are taking, they obviously you have 400 million images. Out of that, at the same time, they select 32,764 examples, right? The reason they need such a large batch size, usually when you're training a vision model, right, the batch sizes are 32, 64, in that range. But here, the objective is very different, right? You want to make sure that in this large space that you're constructing, images which are similar, image and caption pairs which are similar, they are together, and image caption pairs which are not the same, they are further away. So the reason you need that large batch size is that, suppose you chose a small batch size, right? Let's say a small one, which is 32. In that case, the guarantee, you're not checking. You don't know initially, right? You only know that the two pairs which we know. So the man wearing a mask and that image and the text, we know that they are the same, but there could be other examples in the set which are the same, right? If you use a small batch size, like let's say 32, there is a chance that one of those images, which is actually similar to this image, you could have an image of a dog and another image of a dog, which can completely screw up the training process. But if you use a very large batch size, even if there are some mistakes, right? There could be an image of a dog. You're saying that this dog image and that dog image, they should be farther away, right? So even if you do that, because the batch size is so large, there are so many images in the set, it doesn't, the noise level is very low, right? So you could have mistakes where there are two dog images and we are trying to pull them apart, but it still works out because the batch size is that large. They used, mixed precision training, which means that they used both floating point, float 16 and 32. And usually these things are just for, they're used to make some of these things faster, because, GPUs may have certain accelerators, etc., and they want to use this. If you think about it, right, there is another way they could have trained a vision language model. One way would be that you do the next word prediction. So you have an image, you try to encode it, and then in such a way that it predicts the next word in the caption. So you could take an image and try to predict what the caption could be. And that process turns out that it is more expensive. It was, trying to predict the caption, that task is much more expensive, and it was slower to learn the visual features, right? So think about it, right? I mean, just because I told you how this thing is trained, it becomes obvious, right? That we used a contrastive method of separating images and caption pairs which do not belong together. But this was also a reasonable choice, right? Given an image, you predict the caption, right? So caption prediction could have been the way this was trained as well. But the only way we know that that was not a good idea is by trying, right? There is nothing obvious about this not working, right? This could have worked as well, but you have to try and see that, okay, did not work. So that's the engineering part of training computer vision or these kinds of models. you don't know beforehand whether things will work out or not. All right. So limitations of CLIP, it is, it is not very good at abstract or fine-grained tasks, right? For example, if you want to differentiate between two different categories of birds, this is not going to work out, right? So because again, when we are trying to when we train this model, it is based on separating different classes, right, which don't belong together. And if two species of the bird are very similar, it actually doesn't. It's not very good at separating them, right? Um, and then if it is not trained on certain things, then it doesn't generalize very well. For example, it is not able to do classification on MNIST, right, which is a very standard thing, right? Handwritten digits in MNIST. So it doesn't do very well on those, right? And also it is sensitive to prompt phrasing. Of course, we know that, when you're using images at internet scale, there will be a lot of biases. And 400 million images, most likely they were not, part of them could be manually curated, but I'm pretty certain that most of it was not manually created. So it will have all the biases, right, that internet scale data has. So there are some ethical and practical concerns, obviously, because it can be used for it can be used with any powerful model, right, of this scale, because it is trained on internet scale. It can have all kind of nefarious use cases, which there are these ethical concerns for that.
Many,
So
many such cases, many such cases.
yeah, I mean,
Quick, I'm going to butt in
it's
here
a
real
powerful.
quick
Yeah.
to give a shout out to our newest YouTube member joining at the supporter level, Dr. Fatih Tekin.
Okay.
Thanks for
Thank you.
joining us, Doctor. We appreciate it. OpenCV now has YouTube memberships available. You can go to youtube.com/@OpenCVOfficial. It's $2.99 a month. Basically, you get to use the OpenCV logo as an emoji. You get some little flair for your YouTube profile, and you get the good feeling in your heart of helping out a nonprofit organization that puts out an absolutely free computer vision library. So thanks so much for joining us, Dr.
Yeah.
Fatih. We appreciate it.
All right. Welcome, Doctor. All right, so now we are going to go over a tutorial, right? We will go over a tutorial on how to do zero-shot image classification using CLIP, okay? You're able to still see my screen, right?
Yep, looks good.
All right. So as many people in the audience may know, what is image classification, right? In image classification, we have a neural network. The input is an image and the output is a class label. For the entire image is described by a single label. For example, you may have something like an image of a dog. And there are three categories here, right? Cat, dog, and other. The idea is that given an image, you want to assign a label to it, cat, dog, or image. And basically, we come up with class probabilities that this is
Yes, the
yeah,
three genders, cat, dog, and other.
right, right, right. So this is a very standard image classification problem. Now, the problem with this approach is, let's say you had a 10 class classifier that you have trained, right? The way you go about it is for those 10 classes, let's say cat, dog, horse, and so on and so forth, you have to get some certain number of images. Let's say you get 1,000 images per class, right? And then you train a convolutional neural network, and you are able to identify these 10 classes, right? Given an image, it assigns a label to it. Now, let's say a new class comes along, which was not part of your initial set. So let's say elephant was not part of your initial class set. In that case, you now need to collect 1,000 images of elephant, right? Put them in the training set, retrain the entire network, and now you have an 11 class classifier, right? So this can actually take you a few days. You have to collect 1,000 images of elephants, and then you have to train the network. So it can take from a few hours to a few days, right? Depending on how complex the problem is. Now, imagine you could do this task in just a few seconds, right? You didn't have to. Now imagine that you could come up with something where you didn't have to train anything. A new class comes in and zero shot, it just works, right? You just make one little change in your code and it works. So that is the power of zero shot classification using clip. And I'm going to show you that. So
Quick question, Doc. Is this Google Colab notebook available publicly?
I will share it. We
Great.
will.
So we'll stick it in the show notes after the show. There, folks were asking about it in the chat.
Yeah, I will share it. So
speaking of which, before you get started again, this is the most viewers we've ever had on YouTube. There are 71 people watching on YouTube right now. This
amazing.
may be, this is like we just passed 200 peak live viewers. Hokey smokes.
Yeah, I'm so glad to be a YouTube influencer now.
Yeah, I know. The checks will the checks will start coming any minute now. I can't wait to see our first payout from YouTube for like $6.
With YouTube and the OpenCV tariffs, I think we have got it covered. All right.
Absolutely.
So so Clip has many implementations, right? There is the original implementation of Clip, but the most easy to use, in my opinion, is it's part of the transformers package. This is through Hugging Face. Hugging Face has this very nice, if you have not explored it, you should try it. In fact, Hugging Face was a different company before. The way they came to be known is because of this transformers package. When the first transformer architecture came out, I think it was in TensorFlow, and they implemented the PyTorch version of it very quickly and very nicely, and that's how they became famous. This is the package that made them famous. So okay, so we installed the transformers package standard. From the transformer package has many different implementations, pretty much of anything you want under the sky, which relates to transformers. So we are going to import the clip processor and the clip model, and this is used to get the clip model. And there is a preprocessor. I'm going to talk about the preprocessor in just a bit, and then standard display. So we have already talked about this. What is the purpose architecture, how the training is done, etc. Now, clip model, right? We are going to use a pre-trained model, and there are various flavors of clip. Some of them are larger, and this is a popular one, clip VIT base patch 32, right? This means that it is a VIT, means vision transformer. The backbone that we are using, it's a vision transformer backbone. But you could use the ResNet one as well, and it will work fine. So this is a specific model that we have chosen, which is big enough to solve our task, but small enough to run quickly, right? So we get the model, and once you do it, I really like how easy they have made it. You just say from pre-trained, it actually gets all the necessary files, etc., and it's all loaded in the model. Next, we want to do a processor, right? We want to get the processor. The processor does, so the syntax is very simple. Clip processor from pre-train, and we pass in the model name, right? The reason we need the processor is we want to do text processing and image processing. So in image processing, it resizes the model automatically. It does a center crop. It does data type conversion, and it also normalizes, right, the image. So very standard pre-processing steps that you don't have to worry about, right? You load the processor, and it does everything behind the scene for you. Similarly, for text, you need to do tokenization, which means that, as I said, that almost every word is a token, and you have to convert those words into numbers, right? And that is what the tokenization means. And sometimes, to make sure that given different lengths of input, you may want to add some padding to it, and that's also automatically done by the text processor. And data type conversion, etc. Everything is handled by the processor. We should not be doing this by hand, right? I mean, you could do it, but it's always good to use the things that are already provided by the framework. Okay. So here, it's, the processor, we are loading the processor, right? Very simple, clip processor dot from pre-trained, and you pass in the model name. Then then we want to load an image, right? We have this image, which we got from the internet, and this is using PIL. We are simply loading the image and displaying the image. You can see that these are images of cats, right? Now we want to have a classifier for three, right? Cat, dog, and rabbit. And if I want to change this, I could simply add another elephant, and that is all the change I need to make if I want elephants to be part of this classifier also, right? Think about it. I did nothing, right? If I want to add a new class, that's all the change I mean, this is literally the change I will need, right? In my code. So that's the power of zero-shot learning. So now we first do inputs using the preprocessor. We pass in all the text. So this text is this text. The images is this image that we just loaded, right? And then return tensors. So this we want to return in PyTorch format. And if some padding is needed to the data, do it. That's all we are saying in this. Very simple syntax, right? So now let's, we run this, and if you run this, you will see this. It has many different parts, right? So if you look at, we had put in this, the text that we were using is cat. Where is the text? Right here, cat, dog, and rabbit. And this text gets encoded into into a vector of 3. You can see that usually the vectors are pretty large, but because I used a single word, the vectors are, it's just 3, right? And you can see that some of these are same, right? For cat, this is the tokenization, and you can see that it is the first two are the same for cat, dog, and rabbit. And the reason is that this is the start of the string that shows the start of the string. This shows the end of the string. And this is the actual encoding, right? So they are all the same. In fact, if you, I could have also used something like a photo of the cat, a photo of a dog, a photo of a rabbit. That's probably slightly better than using cat, dog, rabbit. But even this will work. Inside the input, we also have something called an attention mask. And this is not very, I'm showing it just because people may be confused what exactly it is. But this, it's a binary mask that indicates which tokens, right? These are tokens, which tokens in the inputs are actually words. But there could, because let's say we use many different sentences, right, of different lengths, then there could be some padding as well. In that case, the masks would not be all one. They would be zeros and ones. Ones would indicate that this is actually part of the sentence, and then you could have some padding as well, right? So that is why the masks are used. Now, the inputs, because we had also put in, our image was also part of the input. We can also look at the pixel values, and if I do this, you will see that the shape of the input is 1 by 3 by 224 by 224. Now, 224 by 224 is the preprocess. After preprocessing, it has center cropped the image. It has removed 224 by 24 is the image size this VIT operates on, right? So that is why you see that is the size of the image. 3 is the number of channels, and 1 is the batch size. You could have used multiple images and done this, at the same time. But for our purposes, we are just using one image because, for demonstration purpose. But this is the batch size, right? So you can see that the image size was completely, I don't remember the image size, but it is definitely not a square. But because the transformer uses a square input, needs a square input, the preprocessor or the processor has already converted this image to the right size. It handled all the data type. It did everything for us. We don't have to worry about it. And it also created this, it also created this, where is it? Right. It also created this shape for us because Torch uses this, it always requires a batch size. So you need to add this extra dimension when you're passing, when you're trying to encode the image. So it did all that work for us without us having to write any specialized code. And that's beautiful, right? But you can see all the image values which are normalized are there in this entity. Now we have created the inputs, we have loaded the model, and we can create the output by simply doing a forward pass on the inputs, right? So we put in the inputs and the loaded model, do a forward pass, and this is how you do a forward pass, you get the outputs. This no grad, it ensures that no gradients are computed. Gradients are usually computed if you want to do training. If you want to do training, if you want to do debugging, then you may need gradient computation. But here we do not want gradient computation, so we are telling Torch, don't bother with gradient computation. Just load the model and run it. So once you run that model, you will get this output, right? The output will contain the text embedding. I'll come to this one, but it will contain the text embedding. It will contain the image embedding. And if you actually print the size of this, you can see that the text embedding, there are three text pieces, right? Cat, dog, and rabbit. So that is why it has three elements here. But the size, the length of the vector is 512. Remember, so we started with tokens, right? The text was converted into tokens, and now it is converted into an embedding, right? An embedding is that point in a multidimensional space, and we want this embedding to be the same as this embedding, right? So this is the image embedding, right? You can see, and now you have an image, right, embedding, and you have three text embeddings. All you have to do is calculate the cosine transform between them and see which one it matches, right? But fortunately, we don't even have to do that because the output, when you run this, it gives you the logits. Logits is basically the output of this operation. And you can see that it gives you these numbers, right? It gives you the cosine distance. And in our example, we have a cat, right? So the first one, you can see that it has the highest value. So the cat embedding has the highest value. Then we have the dog, and I think this is the rabbit, right? So this is the output that we can actually look at the output and do the classification easily. But if you want to build something general purpose, you want to convert these into probabilities, right? The way to convert this thing is into probabilities is to use softmax, right? Softmax basically takes these values. This is the simple formula. And if you, it's not difficult, right? It just looks looks a little bit, it's very standard way of converting logits or the outputs, raw outputs into probabilities, all right? So you can, the way to apply softmax is you take the logits per image and do dot softmax along a particular dimension, and then you get the probabilities, right? And if you print out the probabilities, you will see that the probability of cat is the highest. The probability of dog is next, or probability of rabbit is next, but these are small numbers, right? But you can see that we could do zero-shot classification using this method, right? So no training was involved, as you can see, and this is a general purpose, right? We did not, this VIT that we, this clip model that we got, this was not specifically used for cats, dogs, and rabbit. It just has all this information in the world about various things. And it knows the concept, what is cat, what is dog, etc. And that is why it is able to produce these embeddings. And we are able to see which embedding it is closest to. So we take the image, embed it into this multidimensional space, like 512 by 1, right? And we take all the text embeddings, we embed them also, and we just determine the cosine transform between them, or cosine distance between them. And the one this image is the closest to, right? That is the one we choose as the class, right? As the output. Yeah, so that's zero shot classification, right on time. um,
Yeah, you nailed it.
yeah.
All right, we've got a bunch of questions here, Doc. I think,
Yeah.
though, first we should do our trivia giveaway.
All right.
Yeah, go ahead and unshare your screen for me if you don't mind.
Yeah. 1 second.
Yes, indeed. Wow, that was a whirlwind of a presentation. We've got a bunch of questions from the audience, but first, let's do the OpenCV tradition of giving away an OpenCV University course. The way this works is I'm going to ask a trivia question based on the presentation from Dr. Malik, and the first person to answer that question correctly in the Zoom chat with their messages set to everyone and not just hosts and panelists will win the OpenCV University course of their choosing. You can see what courses are on offer by going to opencv.org/university. OpenCV University courses are industrial strength, industry-ready courses created by professionals, and they really will help you understand, upskill, get a better job, get a new job. All of that stuff is possible with OpenCV University. If you have won in the last couple of weeks, please, or in the last couple of months, please do not answer and give someone else a chance to win. I'm looking at you, the trivia sharks in the audience. Earlier on, we talked a bit, we talked quite a bit about CLIP. How many hundreds of millions of image pairs were used to train CLIP according to OpenAI? Ooh, all right. Man, they were really on that one. The answer was 400 million. 400 million. So the first one I think would have been Bruno
Bruno.
Freitag. Yes. Bruno Freitag, please send one email to phil@opencv.org with the name of the course. You can go to opencv.org/university, find out pick out a course that appeals to you, send me an email with the name of it, and we'll make sure that you get that course in your OpenCV University dashboard. Another one question here, is there a recording of this? Yes, absolutely.
Yeah.
The recorded version of this webinar, along with all OpenCV webinars, will be on the official OpenCV YouTube channel. That is at OpenCV Official on YouTube. I'll drop the link in the chat here. There you go. Yes, congratulations to our trivia winner today. What a day it has been. This is by far the most popular episode we've ever had on YouTube. We hit 240 peak live viewers total
Really?
across Zoom, Twitch, YouTube, and LinkedIn. These were all top days for those platforms, except for LinkedIn, where our viewership's been a little bit lower. But 75 viewers peaked on YouTube. Pretty awesome. Thanks to our friends at Embedded Vision Summit for the boost, I think, on that one. We really appreciate it. Thanks, Phil and Jeff, all right, the homies at EVS, and of course, the Edge AI and Vision Alliance. Questions. You've got questions. We've got answers. I'm looking through here.
There's a question I can see.
This one from Tino Chang was asked this earlier, and I was interested as well. Can you give a simple comment as to why SIGLIP seems to score better than CLIP, but the usage is much lower than CLIP? Have you seen SIGLIP?
I have not.
Okay.
I mean, there are so many vision language
Yeah.
models that I cannot even keep track of all of them. So there are CLIP is okay. The one thing I would say is CLIP is the oldest one, so to speak, right? So anything that comes, one of the things, very obvious things about CLIP is that when they have this vision encoder and the text encoder, there is no cross attention between them, right? They are completely independently encoded, and uh, that when they did DeepMind did Flamingo, they used cross attention, so the results would be slightly better. So I don't know the answer to that specific question, but there could be architectural problems like this, right? Or architectural reasons like this.
Yeah, I just pulled up the archive link. It's sigmoid loss for language image pre-training, 27 March 2023. I've not heard of this one yet. We'll have to let's take a look at it. Reading. Tiana says, so the output classes with this method we were looking at can be essentially anything.
It could be anything. That is what the zero shot comes in, right? And that's very powerful. In fact, it could be not just things, right? It could be, let's say you have food items, right? And you want to say that I have three classes of food items. One is less than 2 pieces, right? The other is less than 10 pieces, and the third one could be greater than 10 pieces, right? So these are quantities, but these are not exact quantities, right? If you want to actually detect the exact quantity of food items, then you will need an object detector. But let's say you just want, rough ideas, right? Then this kind of thing can be done. You can also fine tune a clip model, which will do a better job, right? So you can start with the original clip. So here we did not show fine tuning, right? This was zero shot classification. Immediately you got the answer, but it is also possible. And in the workshop, we are going to show how to fine tune a clip model if you're not getting good results, right? You can fine tune your clip model and get better results.
Yeah, maybe we will have to do a follow-up post Embedded Vision Summit
Yeah.
to tell people about a little bit about fine tuning. Before Embedded Vision Summit, you're just going to have to buy a ticket, folks. Go to Embedded Vision Summit in Santa Clara, California, at the Santa Clara Convention Center. The convention center I've probably spent the most hours of in my entire life. um, what do we got here? A little bit more here. People asking about some more about classes. Yeah. So I think one of the things that was interesting here is yeah, so many questions. Sorry, it's taken me a minute to read these. The Gabriel here says VLMs are more than clip. Are you familiar with any other like when you're in your consulting business, for
Yeah.
example, like what are some of the other ways that similar problems are solved that than simply like using what we showed here?
Yeah.
Obviously, there's always more than one way to do something.
Yeah.
Can you maybe talk a little bit about alternatives or like maybe other things people might try to solve similar problems?
Yeah, so when the okay, so what are one of the disadvantage of using clip, right? Or is that it's a large model, right? It's expensive to run. So if you're not solving a general problem, right, where things are not changing for you, right? Let's say you want to solve a classification problem, you would simply use a convolutional neural network and train a classifier, and that's it. You're done, right? But let's say things could be changing uh, quite different, quite a lot, right? And if let's say for food classification, right? You want to do food classification. What's in my plate, right? So if you want to get this, and you have a rough idea that okay, the food could be um, these are the various ingredients I can have in my food, but you don't know, right? So you could actually run clip, and you have a solution, right? At least you have a solution that works. And over time, you gather, okay, these are the kinds of food items people are asking, uh, us about. And now you have the entire list of different food items that you want to classify, right? So in the beginning, you could use clip to get around that problem that you don't know the classes. But once you have it, then you change it into a convolutional neural network, save a lot in terms of, processing time, etc. right? But uh, Apple has also released something called Mobile Clip, right? And that runs on the device, right? So that runs very efficiently on a mobile device. So very efficient. So that way, there is an expense. It is still expensive to run on the device, right? But not you're not paying the price, right? It is the battery of the device that is being used. So yeah, the obvious ways to run it is using by training a standard convolutional neural network.
Word. Yeah, and a lot of it seems like a lot of the constraints are um, probably around like memory, right? Just the
Yeah,
amount of RAM you've got in there, because at a certain point there's no more for the computer to use.
RAM, and
And so
also if you're running this on the server, if each request costs you, a penny, that's a lot, right?
yeah, yeah.
Versus neural networks, you can run them on the CPU, no problem, right? So it can be very cost efficient to use convolutional neural networks for most of the things, unless there is uncertainty, you just don't know, right? And you want to get something out very quickly, right? So there is always this, you want to get something out very quickly. And in that case, these models like CLIP are very, very effective. By the way,
Yes, of
CLIP
course.
is also used inside Stable Diffusion, right? When they have Stable Diffusion, the image, because you're writing a prompt and an image is produced, to check how good the image is compared to the prompt, they match it using CLIP.
Yeah, it's a sort of a
Yeah,
self supervision of the output of the image model, right? Like it
yeah,
says, is this what does Clip think this is? Like, is it does it how similar is it to what the person actually asked for?
right.
Um, Graham would like to know, what about zero shot for unsupervised classification? If you just specified how many classes there are, is this possible?
Um, you should, I mean, you can
For
obviously use it
example, if
for
you don't
image captioning.
know, if you say there's five classes of items in this image,
No, I mean, you don't even need to specify that, right? How many classes are there, right? You could actually use it for image captioning. Given an image, you can find out what the caption should be,
yeah, it's
right?
sort of
And
like
then
the
interpret it.
opposite of
Yeah.
what they're asking for. Like I think maybe yeah,
Yeah.
it's a bit of confusion. Um, this clip example workbook, this is Vitor here in the chat, says this clip example works quite a bit differently than current 2025 multimodal models seem to work. Can you talk a bit about the more recent sort of upgrades to these sort of workflows?
Yeah. Let me show you something. I wish I had that slide open right now, but let me, where is it? I'm thinking about it. Uh,
That's all right. I'll use this moment to check off one of the check boxes on my to-do list for the show, which is mention the 1995 Catherine Bigelow film Strange Days.
Give me 1 second. Let me uh, find that.
You know, Angela Bassett at the height of her powers. She deserves everything, folks. Got a few more questions. I think we take a few more. We did go a little bit over earlier. You got a hard stop today, Doc?
I do in a few minutes, but I want to find that. I just gave a talk and I cannot find the. Uh, okay, I'll find the paper
It's all
then.
good. People are asking for more information about Strange Days. This is now Phil's movie corner on OpenCV Live. Yes, Richard Harris the film is Strange Days, the 1995 Rafe Fiennes, Angela Bassett, um, directed by Catherine Bigelow. It's a science fiction. It's sort of a hard sci-fi movie, but just really good. Everyone's clicking on all cylinders. I think it was a pretty big flop at the time, but in hindsight, just absolutely whoops ass.
Right. So here, when I say that, vision language models are not the same, right? They are trained for different outputs, right? It's so when you say that, okay, if you are training an image classifier, right? In that case, the black box could be different, right? Inside the classifier, you could have many different architectures, etc. But the input and the output usually remains the same. Input is some image, and the output is one of n classes, right? So that's a very standard problem, right? But when you talk about vision language models, not only does the architecture in between change, in the middle change, the input could change, the output could change, right? So it can be very different. For example, just to give you an idea, this is the input format for Flamingo, right? In Flamingo, this is a model. This is a 2022 or 2023 model from DeepMind. You can see that it uses a combination of images and text as input. And here, the goal is few-shot learning. So here, for example, it shows, I hope people are able to see this, right? So you can see here that it shows a picture of a chinchilla. Right after that, it says, this is a chinchilla. They are mainly found in Chile, okay? Then in the same input prompt, you have an image of a dog. And then it says, this is Shiba. They are very popular in Japan. So if you look at the pattern, it's basically first saying there's an image, and then it's saying what is in the image, and then there's this thing about the location, right? About the image. And so this is few shot. If you do this for two images, it knows, the model knows that the first one, it should respond in two sentences. The first sentence should say what's in the image, and the second image should say something about the location, right? So if you look at this flamingo, it says, the completion it does is it's a flamingo. They are found in the Caribbean and South America, right? So you can see that this vision language model is completely different on compared to how CLIP is trained. And just to give, so this basically takes an arbitrary sequence of images and text and is able to output something. Just like a web page. If you go to a web page, you would see some text, some images, and it's all free flowing. So Flamingo is trained on that kind of free flowing examples. You can also see that here, it's all few shot. You give it an image that this is the input, followed by this is also part of the input prompt. Then you give another image. This is part of the input prompt, and it is able to say, okay, given this image, this is the output it needs to do. So this has been trained for few shot learning, right? You can also expand that idea to videos, because you don't need to provide it the input in a particular sequence. It can be any arbitrary sequence of images and sentences, right? Images and text. So here you can see that you basically provided a whole bunch of frames, and the output you're asking is what happens to the man, right? The answer is he falls down, right? And as I was saying, hopefully, okay, here, this is the way it
It
is
sounds
trained.
like a sign countersign for a 1960s spy movie. Like, what happens to the man when he hits the ball? He
Right,
falls down. All right, you are the agent.
right. So here you can see that how the training methods are also completely different from how CLIP was trained, right? Here, basically, given an image, you have this input image, input prompt, and when they say prompt, it is a combination of images and words. They process and remove all the images, right? And only the text is used. It passes through a text encoder. At the same time, these images that were extracted, they go through a vision encoder, and then they get interleaved with the text encoder to find the output, right? So very different architecture compared to what CLIP was. And if you look at other architectures, they would be completely different, right? So it's very difficult to say they cannot be compared, apples to apples. They are very different beasts, almost. Apart from the fact that they use images and text, there's almost nothing similar between the two models, right? So that's one thing that you have to be careful about while thinking about
That
vision
makes
language
sense.
models. Yeah.
Yes.
And you can imagine that speech is also done in the same way, right? You add another, just like vision is encoded and you get a vector out of it, right? The same thing can happen to speech also. You basically encode speech into a vector, just like, and speech has similarities with text, right? Because they can be of different lengths and such. So speech in the most mind-numbing way, if you want to do it in the most mind-numbing way, you can convert that speech to text and then it becomes the same, right? But speech can be directly encoded just like text and images as well.
That makes sense. I think now we can call it a day, Doc. You want to take us home?
Yeah. Thank you so much for being part of this tutorial. If you want us to do more of these, please let us know. Right, that gives us a signal that okay, we should be doing more of these. And if you are at the Embedded Vision Summit, I would love to see you there. This tutorial would be 3 hours long, and we will cover many more things like fine-tuning of vision language models and 2 different applications. So we will cover 2 different applications, including food analysis that I mentioned. So
Yeah.
that's it from my side. Thank you, Phil, for organizing this. That's it. Thank you.
Yeah.
Thank you, everybody.
Thanks so much, everybody. People are asking, yes, the recording of this is available immediately following the show on the official OpenCV YouTube channel. That's youtube.com/@OpenCVOfficial. You can watch it there. We're also going to add the links to the Jupyter Notebook and all the interesting stuff we talked about here today. Take care of yourselves out there, folks. Take care of somebody else if you can, and have a great day wherever you may be. We will be back next Thursday, 9 a.m. with Kwaban Aguiman from OpenMV.
All right. Sounds good.